Welcome to the Last Bits of Nuclear Energy Screencast. That we've actually already done more or less, but we'll just summarize it quickly. Whenever our nuclear decay is a random event, we can't predict when a specific nucleus is going to radioactively decay, but we do know if we have a macroscopic sample of a radioactive substance, we can describe its decay in general terms. And what we know is that radioactive decay rates, even though they vary a lot from one isotope to another, for a given isotope, the rate of decay is always directly proportional to the amount of that isotope. And as we saw before in kinetics, this is first order reaction. This is first order kinetics. Rate of decay for a nuclide, for a specific nuclear isotope, is characterized by its half-life, which we sometimes symbolize by T sub 1/2, and that's equal to ln of 2 over the rate constant K, or 0.693 over the rate constant K. And this sort of relationship and graph should look pretty familiar because this is just first order kinetics. Here is a summary of the the equations describing radioactive decay. Thing to note is instead of concentration, we often have just amount, so N represents amount, but everything else looks pretty much the same, and we've done this before. Okay. Reminder about half-lives is that half-lives is the amount of time it takes for half of the substance to decay. So in one half-life, it goes from 100% to 50%. In another half-life, it goes to 25%, half of 50. In another half-life, it goes to 12.5%, half of 25, and so on. Here are radioactive half-lives of a number of substances, and if you'll notice, they vary pretty dramatically. Iodine 131, about 8 days. Carbon 14, almost 6,000 years. Uranium 238, 4.5 billion years. And fermium 244, just over 3 milliseconds. And there are some useful radioisotopes that are used in various things. All right. We're also going to note that for a given isotope, it's going to decay when it a radioactive isotope, that is. And when it decays, if it doesn't make a stable product, then it can undergo another decay, and another, and that's going to continue until ultimately a stable nucleus or stable isotope is produced. And here is an example of a nuclear decay series. We have uranium 238 undergoing alpha decay, then beta, then a bunch of alphas, a few betas, alpha, beta, alpha, and it doesn't stop decaying until it forms lead-206 isotope, which is stable. And this is what it's like at the home for old atoms. All right, an example with a calculation, and again, these are things we've done before, but one slight different twist. We'll just do an example. What's the activity of cobalt-60? And just as a note, we often use the term activity for rate when we're talking about nuclear decay. So the activity is the same as the rate. It's the rate constant times the amount of material, where the rate constant is ln of 2 over the half-life. So if we have 5 grams of cobalt-60 with a half-life of 5.26 years, then we can do the calculation. Activity is K times N. K is the same as ln of 2 over the half-life, and then that's times N. 0.693 over 5.26 years. That's that ratio that gives us K. And then 5 grams is the amount we have. And if we do that calculation, we get about 0.659 grams per year. So that's the activity. Now, just as a note, there are other units we can use for activity. And so let's try calculating again, but now convert from grams per year into something like decays per second. So we convert from grams of cobalt-60 to moles of cobalt-60, then from moles of cobalt-60 to atoms, and then from years to days, and from days to hours, and from hours to seconds, and that gives us about 2.1 times 10 to the 14th atoms per second that are decaying. And it's kind of boggling to the mind to note that 0.659 grams per year corresponds to 2.1 times 10 to the 14th atoms per second in terms of decay. Those are the same decay rate in different units. Pretty amazing. Okay, how much is going to remain after 2 years? This should look super familiar, so I'm just going to blast through it. There's our calculation, and there's our result. And then how long will it take until only 1 gram remains? And now again we have to solve this time for t, and that should also look familiar, and there's the result. And then one more slight different type of problem. We often use radioactive decay to date things. So carbon-14 is a radioisotope that has a half-life of almost 6,000 years. We have small amounts of carbon-14 in living organisms. Living organisms exchange carbon with the environment and maintain a reasonably constant rate of ratio of carbon-14 to carbon-12. When the organism dies, though, no more carbon-14 comes in, and the existing carbon-14 undergoes decay, and so there's less and less of it over time. And by comparing how much radioactive carbon-14 we have, which is normally by how much radiation it emits, compared to what a living organism would have, we can determine the age of formerly living organisms, like the plants that made up the Dead Sea Scrolls. So here is our data for this problem, and note, this is the kind of new thing, the number of disintegrations per second or per minute or per hour per amount of time are going to be proportional to how much carbon-14 that's left. So normally living organism carbon-14 decay rate would be 13.6 disintegrations per minute per gram of carbon. The Dead Sea Scrolls have an activity that's less, 10.8 disintegrations per minute per gram. So if we do our calculation in the same way we've done it before, but since amount is proportional to activity, then we can do the ratio of activities, and there's our setup and calculation, and reworking it just a little bit and canceling stuff out, and then the result. So the Dead Sea Scrolls, the plants that made up the material of the Dead Sea Scrolls, those died almost 2,000 years ago. Okay, this is the basis for radioactive dating. Same old story. We met through each other through a carbon dating service. Well, maybe not that kind of radioactive dating. Carbon-14 has been used to, or can be used to determine the age of formerly living organisms, things like the Dead Sea Scrolls or the Shroud of Turin, which is very famous, using carbon-14 with a half-life of 5,730 years. And then we use other methods using much longer-lived half-life elements like uranium-238 to determine the date of rocks. And we'll skip an example of that. But we use much, much longer half-lives because rocks formed much, much longer time ago. All right. Last little bit of stuff here. Note that we're constantly exposed to background radiation from all kinds of things. Cosmic radiation, rocks, medical procedures, and we even have our own atoms. Some of them are radioactive. Now, this can be a problem because if radiation has enough energy, it can knock electrons out of atoms, and in fact, it could even break bonds. But radiation that has enough energy to knock electrons out of atoms is called ionizing radiation because it ionizes things, knocks out electrons. And what often happens is it does this to the most abundant molecule in water, most abundant molecule in tissue, which is water. And what ends up happening is it forms a hydroxyl radical. It basically knocks off a hydrogen atom, knocks an electron off of that, and what's left behind is an OH. And notice this OH is missing an electron. It does not have a full octet. And anything with an unpaired electron like this is called a radical. Those things are very, very reactive. This is true for anything that has an unpaired electron. They're also sometimes called free radicals. And then what these highly reactive hydroxyl radicals can do is they can react with biological molecules, DNA, proteins, enzymes, and cause damage to the molecules and therefore disrupt physiological processes. And so here's sort of an image showing that radiation can break water apart to an OH free radical that can react with something like, let's say, DNA and damage it, or radiation could be even high enough energy to break bonds within the substance itself, and both ways can make damage to biochemical processes via damage to biochemical molecules. Now, radiation can harm the whole body. We call that somatic damage. Or it can harm the reproductive cells, the eggs and sperm, which is genetic damage. And it turns out that the effects of radiation exposure are more damage or are more pronounced on cells that reproduce quickly. Things like bone marrow, embryos, hair follicles, and therefore people who have radiation treatment get achy bones, get nauseated because their stomach lining, which is also something that reproduces quickly, gets damaged, and why you don't want to have radiation treatment if you're pregnant. Oh, and why they lose hair. Now, the effects of radiation depend upon several things. Type and energy of radiation, how far away the radiation source is from whatever is being potentially damaged by it, and how long a time of exposure we have to the source. We measure radiation in a couple different ways, actually more than a couple different ways. One is what's called a rad, for radiation absorbed dose. That measures amount of radiation directly. And then tissue damage depends upon what type of radiation we have, and that's often measured in what's called REM, for Röntgen Equivalent Man, REM. And other units we do for activity, disintegrations per second, which is 1 becquerel is a disintegration per second, or lots of disintegrations per second, we use Curie. Radiation absorbed dose, a rad, is the amount of radiation that puts 1/100th of a joule of energy into a kilogram of body tissue. And then relative biological effectiveness is a factor measuring the relative damage done by the radiation, and that multiplied by the rads gives us the REMs. And that's it for nuclear chemistry, the final screencast.